Question 7, we've been given a graph, and from the graph we've got a temperature change, and then we've made a mixture or carried out the reaction at time 4. That's why we don't have a reading at time 4. So we've got some readings up to time 3 minutes. At time 4 minutes we don't have a reading, and then we've got readings at minutes 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So the reaction's carried out at minute 4. That's why we don't have a reading at minute 4. We need to measure the temperature change when we do that, carry out that reaction, when it first reacts at time 4. So what we need to do is we need to extrapolate this line forward. That means take it forward beyond that point to time 4 minutes, when the reaction's happening. So you draw a line through those 3 points. I'll probably ignore that one. That one seems to be an anomaly. Your line of best fit is through those 3 points, and it'll hit the line there at temperature 23. So the initial temperature at time 4 minutes, is 23. There. Then it goes up and comes back down here. The reason it doesn't shoot up the temperature straight to the top is because there's a little bit of a delay on the actual thermometer warming up and taking these readings. So what's actually happened is, if you extrapolate this line backwards here, this line of best fit, ignore it where it's coming up slowly, take this line and extrapolate that back to line 4, time 4, it probably hits the time 4 at about that point there, temperature 40. So this line extrapolated comes to 23 degrees Celsius at time 4, and this line extrapolated back hits line 4, time 4, at about 40 degrees C. And so if you draw those two extrapolations back, a line back there and hit that at 40, a line forward there to hit at 23, you'll find that the temperature change, 40 take away 23, is 17. The student used 240 milligrams of magnesium and 10 centimeters cubed of trichloroethanoic acid. Use these data information to calculate the enthalpy change. Now, I've been given a specific heat capacity. The only reason that I've been given a specific heat capacity is to use Q equals minus MC delta T. Q is the heat change, the enthalpy change, sometimes known as delta H. So if I do that then now, two extrapolations give a temperature change at the 4th minute of 17 degrees C. Q equals MC delta T. There should be a minus in front of that, really. We can add the minus at the end. The mass is 10 centimeters cubed of aqueous. Aqueous means it's mainly water. So you should know that water has 10 centimeters cubed is the same as 10 grams. 1 centimeter cubed is 1 gram. It's got a density of 1. So 10 centimeters cubed is 10 grams. The mass of the solution, you look at the mass of the water, the liquid, not the mass of the magnesium, the mass of the liquid, the water that you're heating up, that's getting heated up in the reaction, is 10 grams. C is your specific heat capacity, which is 4.18. That's why we know, being given a specific capacity, that we're using this equation, multiplied by temperature change, delta T is 17, and it comes out as 710.6 joules. Okay, now that's going to be exothermic, because we know that the reaction is getting hotter, and that's why there'll be a minus in front of it eventually in a minute. Moles of magnesium. So to do moles of magnesium, you take the moles is mass divided by the MR. So milligrams needs to be in grams. So moles is mass in grams divided by the MR. Turn milligrams into grams. Milligrams is smaller than grams, so to turn a small number of units into a larger number of units, you divide by 1,000. So 240 divided by 1,000 is 0.24. That's the number of grams of magnesium. And I've got its MR as 24.3, so my moles of magnesium is 0.00988 moles. So in other words, 710 joules of energy is given out when we react 0.00988 moles, I need to work out how many joules of energy or kilojoules of energy are going to be given out when we use 1 mole. Well, this small amount, less than 1 mole, gives this, so we're looking for a larger number. So what you do is you take the 710.6 and you divide by this, and it'll give you a larger number. So 71923.06 joules for every mole of magnesium that are reacted now. So we now know the number of joules that would be given out when we react 1 mole of magnesium. We make it minus, we divide by 1000 because joules into a larger unit, kilojoules. Joules into kilojoules you divide by 1000, so it turns out as 71.92307. It's a minus number because it's exothermic, and it needs to be to 2 significant figures because some of my other values, such as 10 or 17 rather, so my 17 here is to 2 significant figures, so we'll take it to 2 significant figures, minus 72 kilojoules per mole.